In this video, we're going to be looking at how to solve for the eigenvectors once you already have the eigenvalues provided. So we're going to be looking at a 2 by 2 matrix, and we're also going to be looking at a larger matrix as our example. So our first example, we're given this matrix 4, 1, negative 30, negative 7, and lambda is equal to negative 2. So since this is provided for us, we don't have to find the characteristic polynomial and do this for every possible eigenvalue. We don't have to find the other eigenvalue. We just have to use the one that we're given. So in order to find the eigenvector, remember we need to satisfy the system A minus lambda I. And that basically results in subtracting lambda off of our diagonals. So one thing to be careful of here is since lambda is negative, subtracting a negative means we add 2. So 4 minus a negative 2 is 6. And negative 7 minus a negative 2 is negative 5. And the other two components don't change. And then we have to essentially row reduce this matrix. Now, it's quite clear in the 2 by 2 case that this bottom row is negative 5 times the top row. So you can already see that they're dependent. And so for a 2 by 2 system, I often don't bother doing the row reducing because I know what it's going to end up with. You can't skip this step when you have a 3 by 3 or larger matrix. But for a 2 by 2 matrix, assuming you haven't made any arithmetic mistakes, these two equations must be multiples of each other. So in any case, this reduces to just this top equation. Now, once we have the reduced matrix, then we extract this equation out of the matrix. Remember that this is a homogeneous system because we moved our AX times lambda x, we moved everything over to one side of the equation. So everything is set equal to 0. So we have our 6x1 and 1x2 is equal to 0. And then because we have only the one pivot, x2 is our free variable. And in order to proceed from here, what we'll do is solve for x1 in the first equation. So we move x2 over, and then we divide by 6, and that gets us negative 1/6 x2. And then our free variable expression gets restated for our new system as x2 equals itself. So the free variable is whatever we declare the free variable to be. In this way, we have our vector components x1 and x2 on the left, and then we just have coefficients of x2 on the right. And so all we have to do is pull out our coefficients, multiply by x2, or typically what is done for eigenvalue problems is we will rescale the vector using a parameter, and we choose a value for our x2 variable for our parameter that is going to make the resulting eigenvector contain relatively small but whole numbers. So in other words, we would try to get rid of all the fractions if we possibly can. So in this case, I'm going to declare x2 to be equal to 6. And if I do that, then my parameter will be any scaling factor of that, and my vector will be negative 1/6. I can also choose x2 to be negative 6, in which case s would be equal to negative t, but I can move the sign around in that case. But any multiple of this vector or this vector are fine in terms of a solution. It's just that when we try to work with these in later problems, it's generally better to work with whole numbers than with fractions. And so one of these rescalings is usually preferred. All right, so let's look at a slightly bigger example with a larger matrix. Now, in this case, we have our matrix here is a 3 by 3. And again, we're provided with the lambda, so we don't have to go and solve for the characteristic equation. We're just going to try to find the eigenspace or the eigenvectors that are associated with this particular eigenvalue. So as we did with the previous problem, we're going to subtract -4 from the diagonal everywhere. So 1 minus a -4 is going to be 1 plus 4, so it's going to give us a 5. 1 minus a -4 is also going to give us a 5. And then -9 minus a -4, -9 plus 5 is -5. Now, in this particular matrix, what you end up with is the bottom row is an exact copy of the top row, and the middle row is a constant multiple of the top row. Now, this does not usually happen this cleanly, but in this particular case, lambda equals 4 was apparently repeated at least twice because we're going to have two free variables and therefore two eigenvectors. It's a two-dimensional eigenspace. If you have only a one-dimensional eigenspace, then it usually is going to be less clear that there are just multiples of each other here. The third row will be some linear combination of the other two rows because you'll still get two pivots and only one free variable. But in this case, we ended up, when we row reduce this, we ended up with one pivot and two free variables. Now, again, we're going to pull this out of our homogeneous system. The top equation, x1 minus x2 minus x3 equals 0. With x2 and x3 free, we rewrite these as x2 equals itself and x3 equals itself so that we have x1, x2, x3 all on the left side. And then we move in the top equation our free variables over to the other side. And then we collect our coefficients for x2. We have 1 and 1 and no x2, so 1, 1, 0 is our vector for x2. And for x3, we have a 1, no x3, and then a 1 x3, so 1, 0, 1 times x3. And again, this is a homogeneous system, so there's no constant on the end. It's just these two vectors. Both of these are eigenvectors for lambda equals -4. So if I were to take 1, 1, 0 and multiply it by the original matrix, I should get -4 times the original matrix. If I take 1, 0, 1 times the original matrix, I should get -4 times the, times the original vector. And if I take any linear combination of these two vectors, if I multiply it by the original matrix, I should get -4 times whatever that original vector was. As long as it's a linear combination of these two vectors, then it's going to be in the eigenspace for -4 as the eigenvalue. So the eigenspace is the span of these two vectors. And again, that means any linear combination, the first vector, the second vector, or any linear combination of those vectors will result in the matrix acting like a -4 multiplier.